Okay, the video is about the derivatives of logarithmic functions. We're looking at natural logs, so that's what I mean by natural logarithmic functions. It doesn't mean they grow in a forest. We're talking about ln natural log. Okay, so there's a theorem that shows that dy dx is 1 over dx dy. Now that might seem familiar based on this algebraic identity, a over b is 1 over b on a, but that's not a proof. Okay, if you go back to differentiation by first principles, there is a way of proving this theorem, so that's beyond the scope of this video. The video aims to look at just a quick derivation of where the derivative of log x comes from. And by the way, when I say log x in this video, it means log x, ln x, or log to base e, natural log. It'll show where it comes from, but it won't be an exhaustive proof. Again, that's beyond the scope of this video. So let's start with our natural log of x, and I'm going to write it more conveniently as y equals log to base e of x. And so that would mean that using our log laws, our definition of a logarithm, x equals e to the y. You might remember that because that's how we define a logarithm. So that's previous work, so we need to go back to our early work on logs if we can't remember that. What we're going to do here is we're going to take the derivative of both sides, and by that I mean, be careful here, this is not an error, dx dy, because here the independent variable is y. Okay, so the dependent variable is x, so it's different to what we normally see. Now the derivative of e to anything is itself, isn't it? If we remember back to, y equals e to the x, the derivative is e to the x, okay, for simple functions of x. Okay, don't get that confused with what we're doing now, but that's the process only. So that's not what we're doing now, because we have x equals e to the y. So the derivative of x with regards to y is still e to the y. From the theorem here, in the maths we're doing, we state that as an obvious result. It is a theorem which we don't need to prove in the subject we're scheduling this video towards. So inverting or finding the reciprocal of both sides, we would have this dy dx now equals 1 over e to the y. Now since in yellow there x equals e to the y, we can make a substitution, so dy dx is 1 over x, and that's our result. The derivative of natural log of x with regard to x is 1 over x. So that's our result there. As an aside, have you ever wondered, now I'm going to talk, if you've watched this video, you've probably done a little bit of integration, and this video is not about integration, but if we look at that, have you ever wondered about the following? And this might premise what you learn later on. You see just some quick examples there of integration that you would have seen. Just some simple polynomials. So integral of x squared is x cubed on 3. Integral of x is x squared on 2. Integral of a constant is the constant times x plus c. That's shown there as c times x to the 0, which is 1. What about if we go a stage further? We notice the power of x drops by 1 each time. What about if we've got negative 1 there? So what's the integral of x to the negative 1? By the way, that's like saying what's the integral of 1 on x? Does it link to that going backwards? Well, let's try the polynomial way of doing it. We would then go, we add 1 on, so that's x to the 0 divided by the new power, divide by 0. Oh, we've broken maths. So that's not going to work, is it? So that's in fact our answer. While it's not a proof, it does show that there actually is an answer. You can find you have to look at it in a completely different way, and there's no room in this video for the theorems, but basically the integral of 1 on x is possible. The answer is log x plus c, but that's in the future. That's a little aside to the video. How do we do questions around this here, the derivative of log x equals 1 on x? Before we do that, I'd just like to show you some graphical evidence that suggests that basically the derivative of log x is 1 on x. We can see log x plotted there in blue, and 1 on x, the derivative, is the gradient function. We can see that that does make sense, doesn't it? Because if we analyze the behavior, we can see that the blue function has a positive gradient here, all the way from apparently the x-axis, even though it might be asymptotic. We basically have a positive gradient the whole time, and the graph for 1 on x is positive the whole time, so it never seems to cross the x-axis. That's good. And we can also see that the gradient is positive but decreasing, and this value of 1 on x is positive but it is decreasing, and this one seems to become asymptotic, log x, and this one here is asymptotic as well. So it kind of makes sense graphically too. Without racing too much of a sweat and using our existing knowledge of the derivatives, we can differentiate all of these here. Remember, we might have to call on the chain rule, product rule, quotient rule, but also something as simple as this, that if we have a constant times a function, the derivative is the derivative of the function times the constant. We've seen that with polynomials. So for this one here, dy dx equals 4 times the derivative of log x. That's what I mean. And that's 4 times 1 on x, which is 4 over x. Second example, y equals log of 4x. Now that is a different question to the first one. Okay, it's actually a chain rule question. Probably not a difficult one by now, but remember, you've got an inner function. I'll do it the long way, but some of you watching this could probably just do this, because that's y equals log u, where u equals 4x. We've done a lot of chain rule. And du dx, the derivative of the inner function, is 4. The derivative of the outer function, dy du, is 1 on u. Okay, because it's basically finding the derivative of log x, except for we have u. And so that means by putting it all together using the chain rule, dy dx equals dy du times du dx, which is 4 over u, unsubstitute 4 over 4x, which is 1 over x. Wait a minute, isn't that interesting? That's the same result as that. Fascinating. There was no mistakes made either. That's true. So that will be the case for any k value here. The derivative of log kx, so the derivative of log kx equals 1 on x. You think about it, if you change that number to anything else there, all you'd have is it changed correspondingly there, which means it would change on there. However, it's counted by that one there, and you'll always have 1 on x. Fascinating. So that's a interesting one. So we've got log of x to the 4th plus 1. So log of x to the 4th plus 1. This is another chain rule. Alright, so I'm going to use u again. Let y equal log of u, where u equals x to the fourth plus 1. Get the gist? Especially if you've done heaps and heaps of chain rule, this is more of the same. So dy du is 1 on u, and du dx is 4x cubed, and dy dx using the full chain rule now is dy du, which is 1 on u, times 4x cubed, which is du dx, unsubstitute, and we've got x to the fourth over 1, we've got 4x, that should be a bigger one, x to the fourth plus 1, and that should be 4x cubed. The last one is a special one, especially if you do a specialist maths as well. It says y equals natural log of some function of x, so some generic function. So we're going to get some general result, and it is a significant one. So we just go about what we do. Alright, so we let y equal log of u, where u equals f of x. So du dx make that neater. Du dx equals f dash of x. The derivative equals the derivative, and dy du equals 1 over u. Alright, so using the entire chain rule, dy dx equals dy du times du dx, which is 1 on u times f dash of x. Alphabet soup, you might say? Hang in there, because that would be, that's a dash, that would be f dash of x over u. Unsubstitute now, u back up there equals f of x, so it's f dash of x over f of x. That's a significant result. If you don't know why now, it is one to always look out for. And also for the integral too, if you take the integral of that, it actually is a very handy rule, and it's a very handy result. So the derivative of the log of a function of x is the derivative of that function of x over the function of x. Hence, to end the video, I'd just like you to note those last two results which build on the first one. So if you've got log of kx, k is a constant, it doesn't matter what the constant is, whether it's 1 or something else, you end up with 1 on x when you take the derivative. And if you have y equals log of a function of x, the derivative is the derivative of the inner function divided by the inner function. Okay, two significant results. Yay!